Hi everybody, we got a conical pendulum problem here. So we've got a pendulum rotating in a cone. It's got a string of length L. It's at an angle theta right there that the string makes with the vertical. They say that the amount of tension is capital T, and we're gonna answer all these questions in terms of L, theta, and T in fundamental constants, which is gonna be little g, acceleration due to gravity in this one. So first off, kind of an easy one here. They say on the figure below, draw and represent the forces on a free body diagram. So we've got the force of tension right here, and then we have got the force of gravity. And I know on all of these that the force of gravity should be basically equal to the vertical component of the tension right there. So there is our free body diagram. And I'm gonna sort of, that's all you wanna add there. You don't want on yours to draw actual components. But because the components are so important, I'm gonna use that right here on this spot. So let's draw this here. And we've got two triangles that are similar triangles. We've got one that's tension, right? And we've got this angle theta right here. And we've got another one where we have the lengths, and that's L. And this angle's also theta right there. Each one of these is going to have a vertical component. So this one is Ty, and we know that Ty has got to be equal to the force of gravity. This one right here we can call Ly. That's not really going to wind up being important in this problem. Then we've also got this component here. We could call this Tx, and that is the centripetal force there. So that's the one causing it to go in a circle. And then we've got this length right here. We could call this Lx, and that's actually the radius in the problem. So we got to keep that in mind as we go through here. All right, so now to get the weight, we know that the tension in the y is equal to the force of gravity. So we can say this, tension in y is equal to Fg. And then we can expand this out. Since the tension in the y is the side touching the angle, that is going to be a cosine function. So T cosine theta is equal to mg for the force of gravity. And then we simply rearrange to solve for mass. So mass is equal to T cosine theta over g. And we've got our mass in terms of T, theta, L, and physical constants. All right, next up, it says determine the speed of the ball. So a very understandable dead end that people are gonna get to is they're gonna say that the velocity is equal to the circumference over the period. Although here, that we're using T for tension, so I'll use a P for period. So velocity is equal to circumference over period, and that would be equal to 2 pi r over the time. But we don't have that time. We don't have any information about that time. So that's not gonna work. We run into a dead end. So here's what we gotta do. We can also show velocity with our centripetal force equation. So the sum of the forces is equal to mass times the acceleration. Since this thing is going in a circle, we know that we have to have a centripetal force. And so we've got to have the tension in the x direction is the one that causes it to go in a circle. And that will be equal to mv squared over r there. So now I'm gonna solve this for v. I'm gonna multiply my r up there. And so I'm gonna get Tx times R. I'm gonna divide my M down there over M, and that would be equal to V squared. So I gotta take the square root of all of that, and that is equal to V. Now be careful, because we're not actually okay here, because there's a lot of things that are not allowed. Tx is not allowed, R is not allowed, M is not allowed. So we've gotta go through and replace each one of those. So first off, Tx, if we look at our picture here, on this one right here, our Tx is going to be, since it's the side opposite from the angle, we're gonna use T sine of theta. So I'm gonna replace Tx with T sine of theta. I'm gonna multiply that by the radius. As we talked about before, the radius is the Lx, which is also the opposite sign. So this is gonna be L sine of theta will give us that value. And then we're going to divide by m. But m, if you remember, is this fraction right here. And so since I'm dividing by a fraction, that's the same thing as multiplying by its reciprocal. So I'm just gonna flip this whole fraction right here. And so all of this basically multiplied by g over T cosine theta. And all of this, right, is underneath a square root there. So now, that's it. And you could leave it there and that would be an answer and they would have to take it. Let's clean it up a little bit. You could pull these two sines out, that's one way to do it. Or you could look at it as a sine over a cosine becomes a tangent. Oh yeah, and here, a tension there and a tension there is gone. So if we do that, then we can see I'm still gonna have an L here and a G here. I'm gonna pull those up front. So LG, one of my sine thetas is left. This sine goes over top of that sine and is gonna give us a tangent theta. And I actually think it's cool when something simplifies down so much like this, where if you spun any conical pendulum in a circle and you knew the length of the string and knew the angle that it made, you could calculate the velocity that it must have based upon that. All right, so last part here is it says determine the frequency of revolution of the ball. So now here, that other equation is going to come back. The one that we tried to use potentially before, that velocity is 2 pi r over the period. So the distance we go, the circumference over the period. So I'm going to multiply my t up here. I'm going to bring my v down there. So t equals 2 pi r over v. Now remember that we want the frequency though, and frequency is equal to 1 over the period. So I simply need to flip my fraction right here. And so since I'm 1 over the period, so my frequency now is going to be equal to v over 2 pi r. And now I've just got to plug in with the things that I had before. So my velocity, remember, was from our previous one, the square root of LG sine theta tangent theta. And we're going to put that over top of 2 pi r. But be careful, remember, you cannot put r in there. We've got to use it in terms of L. So r is the Lx component, which is L sine theta, since it's opposite to the angle. So this becomes L sine theta.